Okay, I think we'll get started. So today we're going to use some of our knowledge now of harmonic motion to talk about the vibrational motion of molecules. And we'll throw in translation of the molecules and rotation so that we can characterize molecules in terms of their degrees of freedom, as they're called. So we know that eventually we're going to learn about molecules in a more sophisticated way using full-blown quantum mechanics. But again, we can often utilize the simple classical mechanic ideas to gain a lot of intuition about molecules. And in fact, you can do a lot of organic chemistry just by thinking about molecules as masses on springs. And we can learn a lot about the behavior of many compounds that way. All right, so let's use water as the working example. So water has 3 atoms, oxygen, 2 hydrogens. And to be just completely naive about things, let's just let each atom move, right? Because we know the bonds can stretch, the whole thing can rotate. So let's just let each individual atom move in its own coordinate system. In viewing it that way, we expect that oxygen will have 3 degrees of freedom, DOF, degrees of freedom, and that's the oxygen can move in the Z direction, the Y direction, and the X direction. Likewise for both of the H's. So 3 degrees of freedom here, and 3 degrees of freedom here. So that gives us a total of 9 degrees of freedom. So if we let each atom move, then we should get 3n degrees of freedom for an arbitrary molecule. And that gives us a starting point to know how many total degrees of freedom the molecule will have. But now we want to categorize those degrees of freedom as translations. And in translations, the entire center of mass of the molecule moves. In rotations, the center of mass of the molecule doesn't move. The relative positions of the atoms don't change. There's only rotation about the center of mass. And then finally, vibrations is when the center of mass does not move. There's no rotation, so there's no any kind of angular motion to the molecule, but there are changes in the relative distances between the atoms. Those are called vibrations. So let's start with translation. Now, here's water. I've indicated with a blue dot here the center of mass. And then we use, I'm using green arrows here, we're using arrows to represent the motion of the atoms. And so we can think about the case when all 3 atoms are moving in the Z direction. Then what's going to happen? The molecule will stay intact and just the whole thing will move. So this is representing center of mass motion in the Z direction. Likewise in the Y direction and coming at you in the X direction. And that's it. Of course, the molecule could be shooting off at an angle, but we can decompose that motion into its 3 components, X, Y, Z components for that motion. And so there's always going to be 3 translational degrees of freedom for a 3-dimensional space. If somehow we're thinking about molecules in 2D, then there would be 2 dimensions, or 2 degrees of freedom for translation. So if we're, say, restricting to a surface or something, we have to think about the geometry of the space we're interested in, and we just have the number of degrees of freedom of translational motion as the dimensions of the space. Okay, well, that's translation. Now, I should say I should have noted this here. The pluses mean the atom is coming out of the board, and if we were to have minuses, the atoms would be going into the board. All right, well, let's look at rotations now. So we said a rotation is when the relative positions of the atoms stay the same, but the atom and the center of mass stays the same, but the atoms move or rotate about the center of mass. And again, we can break down any rotation into rotation about the X, Y, and Z axes. So if this is our water here, if this is our z-axis, then a rotation will come out at you. This hydrogen would come out at you, or I guess the way I've drawn it here, this would go back and rotate this way. Now, this rotation and this rotation are the same. They're just in opposite directions. That would be akin to moving this way in the y direction or moving that way in the y direction. Here we're rotating about the x-axis, and so we've got our molecule rotating this way. And then finally, this is rotating about the y-axis, so it's tumbling forward, or I guess tumbling upward like this, like that. So the water's tumbling upward. So now, you would anticipate that there will always be 3 degrees of rotational freedom here, x, y, z. But that's not the case for linear molecules, because we always treat the nuclei of the molecules as point masses, so there's no width to them. So imagine this pen here is a linear molecule, and it's infinitely thin here. It's this long, but there's no thickness to it. So if I rotate it, there's no motion about the center of mass in this axis. So we have 1 less degree of freedom if the molecule is linear. So we would have 2 degrees of freedom for linear molecules. All right, so the remainder then are vibrations. And so let's take the case of water. Water's not linear, so it's going to have 3 rotational degrees of freedom, 3 translational degrees of freedom. There's a total of 3 times 3, or 9. And so we have 9 minus 6, or 3 vibrational degrees of freedom. So let's see if we can identify those. Well, we can have a stretch in which the hydrogens go away from the oxygen in concert, or together, symmetrically. So that's called a symmetric stretch. Notice there's no rotational motion and there's no bulk translational motion. It's just the relative positions of the atoms are moving. So oxygen's going up a little, just a little, and hydrogens are going out a lot because they're a lot lighter. Center of mass is up really close to that oxygen. Then we can have the kind of the opposite. So an asymmetric stretch like this. And it would be okay to call this an anti-symmetric stretch as well, but typically it's called an asymmetric stretch. Typically the symmetric stretch is labeled as Greek letter nu1, anti-symmetric or asymmetric as nu2. And then finally, we have kind of a bending motion of the water, like this. And so that's a bend, it's called a bend. So we have symmetric stretch, anti-symmetric stretch, and bend in water, nu1, nu2, and nu3 respectively. And that covers all the motion of water. So if water takes some kind of a collision, a water molecule, say a water vapor, and it's just going off in space, it might be vibrating in some crazy way, rotating a little, and moving along. And so any of its motion, any arbitrary motion of that water can be broken down into these 9 degrees of freedom. So we can say there's this much component of this type of vibration, this type of vibration, this type of rotation, this type of translation. So in a sense, it becomes kind of a 9-dimensional vector in a way, in that you're taking the whole motion and decomposing it into these sort of basis motions. Now, the vibrations in this setting are referred to as normal modes, and they involve motion of the whole molecule. Now, sometimes certain normal modes have atoms sitting still, but by and large, they involve more than one molecule. It's sort of it's talking about the whole molecule at once. Those are called normal modes. Let's just do a couple of other examples. Let's say we have carbon dioxide. That is CO2, so there's 3 again. But it's different if we draw the Lewis structure here. And then the geometry, it's a linear geometry. And so it would be a D infinity H point group. And we have then 3 times 3 is 9, but since it's linear, we have only 2 rotational degrees of freedom. So that means we should have 9 minus 5, or 4 vibrational degrees of freedom. So it should have 1 more vibrational degree of freedom than water does. Well, it has a symmetric stretch like water, it has an anti-symmetric stretch like water, and it has a bend like water. But if we think of the molecule, it can bend like this, right? Like this, and it can bend like this. And so it has 2 bending modes, and these are just rotated 90 degrees from one another, but they are distinct modes. They're the same frequency, and therefore the same energy, and so we say that these are degenerate normal modes. So there's 3 distinct frequencies, 3 distinct energies. One of those is doubly degenerate, we would say. Finally, let's look at a molecule called benzene, C6H6. Won't draw it out, but you can Google it if you would like. But mainly here, we just want to figure out how many normal modes of vibration do we have. Well, we have 12 atoms, so that's 3 times 12, or 36, minus 6, and we have 30. So, well, yes, it's definitely bigger than water or carbon dioxide. It's still a modest molecule as molecules are concerned, and the vibrational number of vibrational normal modes goes up considerably. So you notice we're always stuck at 3 translation, either 3 or 2 vibrations, and so where every atom we add in, we get 3 more degrees of freedom, so we can quickly add up a total number of degrees of freedom. It can get pretty high, and so we end up with most of those being vibrations. All right, and then let's close here with a special type of this arbitrary motion. So we've said that any kind of a vibration, or any kind of motion, total motion, but let's say any kind of crazy vibration can be represented as a breakdown into the normal modes. Well, there's a very important case of that, and those are called local modes, and that's when the vibration is localized to a single bond. And let's see how that decomposition happens. So let's work with water first, and let's take the new 1 plus the new 2, and we get a cancellation. See, we get a cancellation of the stretch and the compression on this guy, but an augmentation of the stretch, because here they're both stretching in phase here. And I should have mentioned this. We draw the arrows to, well, let's see, we draw the arrows here to represent one phase of the vibration, which was probably clear to you, but so we draw the arrows out, but of course then they come in, out, in. We only draw one phase of that. So we've highlighted this side of the molecule. Okay. Well, how do you think we would get the other local mode where this one was vibrating? We would simply take the subtraction. So we could say new 1 minus new 2. And if you look at new 1, when we say subtraction, what that means is we flip the phase. So that would be drawn this way. The red that I drew there is negative of the green. All right, let's look at just one more example here. Let's do a negative. And so let's subtract the anti-symmetric and symmetric modes of carbon dioxide. And these are, we're talking about the phase where both the bonds are getting longer. We have this one getting longer, this one getting shorter, but we're subtracting it, so that reverses the phase. And so that's going to isolate a local mode on that side of the molecule. And while local modes are, I guess, a little less fundamental than normal modes, they certainly are very important in some areas of physical chemistry where you're trying to understand what things are doing. One particular thing that we think about in our lab is how lasers, if you shine a laser light into a clear liquid, most of the laser goes through, but some of it gets absorbed. And it turns out it's getting absorbed into higher harmonics of these vibrational modes. And it turns out that the so-called free OH local modes are important in that process. So when we look at water, there's a bit of water molecules are hydrogen bonded, a bit of water molecules are not hydrogen bonded. And we've learned now that for the laser light that we're using, the heat is dumped into the local modes of the non-hydrogen bonded waters. And so this type of analysis, which is, a simple analysis based on just an extension of the harmonic oscillator and just thinking about how these atoms can move, and certainly no quantum mechanics, still is important in sort of modern analysis in physical chemistry and physics. So always important to really get down our basic fundamentals, and that's of course the goal of these first three classes and this lecture as well.